Bismillahirrahmanirrahim. I welcome you to the course of Digital Image Processing, and today is our 11th lecture. So today's topic is image transformation. We will go a bit in detail and see some mathematical formulation for transformation. But before going into today's topic, we will summarize the previous lecture. So in the previous lecture, we were looking for image interpolation, and we were explaining it, how does it work and what is the importance of it. And then after that we learned that how to perform the operation of interpolation in a single dimensional image or a signal, or if it is a two-dimensional image or a signal, then how do we manage it. And after that we also learned the unitary matrix and its equation, and then how to apply unitary matrix with the one-dimensional signal and with the two-dimensional signal. So we will continue and use the unitary matrix in today's lecture and see how it can be performed. And for today's lecture, our topic is to analyze the computational complexity of image transformation operation. So in that situation, how do we have this complexity and how do we resolve it? So how to make it easy for processing. And then for that reason we will study separable transformation equation and how do we have this separable transformation of a matrix and signals. And after that we will also see the computational complexity reduction of the separable transformation. So with this separable transformation, how can we reduce the complexity which is now which will be in n4 dimensions, or the complexity will be of order n4, but we will try to reduce it and we will see how do we do it. So if you remember in the last lecture what we did, we learned that if we have a one-dimensional sequence of discrete signal sample, then how do we represent it? We represent it as a UN, where n is actually less than or equal to 0 and less than and equal to capital N minus 1. So now this is a unitary matrix of one-dimensional discrete sequence is given by. So how if this is our the signal in a discrete way, then if we want to represent this as a sequence of signal, then how do we do it? We say that we have a V is a C equation, and V is equal to A times U. So this is a unitary matrix, and this A we call it as a unity matrix. So in the last lecture we explained this. And then if we want to represent this as a form of a matrix, then this can be represented as V of K is equal to A Kn into UN, and then we have a summation of it, n equal to 0 n minus 1. So now this is a simple input discrete sequence, and we said that this transformation is a unitary matrix transformation if the matrix A is a unitary matrix. So the matrix A will be a unitary matrix if it obeys the relation that inverse of the matrix A is equal to A conjugation transpose. So this we learned also in the previous lecture, that what we call a unity matrix is if it obeys one certain rule, and this rule is if we take A inverse, if it is equal to A conjugation of transpose. So if it obeys this, then we say that A is a unity matrix. So this is if we take the elements that they should equal to the inverse matrix of A itself. So also the relation is true for A into A conjugation. So if this is true, then for sure we also know that this A conjugation and transpose is equal to A conjugation transpose A, and this is also equal to identity matrix. So this relation is also true. Now once we have this transformation and we get the transformation coefficient Vk or the transformation vector, we should be able to get back the original sequence Un. This we also learned in the last lecture. So this original sequence is obtained by a similar relation which gives by a U is equal to normally A. So how do we do it? So we say that we have a U and we take A inverse and vector. So this shall be equal to A inverse V, and in our case, since A inverse is same as A conjugation transpose, so this can be A conjugation can be written as A conjugation transpose and V, and this expression can be extended as Un is equal to summation V K A conjugation Kn, where K varies from 0 to n minus 1, and n is less than n equal to 0 and less than n equal to capital N minus 1. So this is in case of one-dimensional sequence. Now let us see what will be the case in case of two-dimensional sequence. So this was the basic that we learned, that if we have a simple equation for single dimension, तो हमने ये देखा था कि अगर हम एक यूनिटरी मैट्रिक्स लेते हैं तो वो हमारे पास, हम उसको एक्सप्लेन कर सकते हैं कि हमारे पास हमेशा जो ओरिजिनल वैल्यू है वो u, हम उसका अगर a का इन्वर्स लेते हैं और वो वेक्टर जो हमने यहाँ से जनरेट किया था ये वाला, तो हम इसको दोबारा ले सकते हैं, ठीक है। तो अगर हमने ये जनरेट किया, जो ट्रांसफॉर्मेशन थी हमारे पास जो यहाँ पर आ गई थी, तो अब हम अगर इसको दोबारा लेना चाहेंगे तो हम सिंपली उसको a का इन्वर्स ले लेते हैं और v के साथ उसका डॉट प्रोडक्ट ले लेते हैं। अब ये हमारे पास जो है सिंपल सिंगल डायमेंशन में है। अगर हम मल्टी डायमेंशन में जाते हैं तो टू डायमेंशनल सीक्वेंस में क्या होगा? सो फॉर टू डायमेंशनल सीक्वेंस द सेम ट्रांसफॉर्मेशन इक्वेशन विल बी ऑफ फॉर्म v k and l is equal to double summation v k into a conjugation kn, and this m and n starts from 0 to n minus 1, and also the k and l also varies from less than equal to 0 or less than or equal to capital N minus 1. So these are the values for two-dimensional signal. So once we have two-dimensional signal, then we can have, as we have rows and columns, so we can represent it like this. So now in the same manner we can have the inverse transformation, so that we can get the original two-dimensional matrix from the transform coefficient matrix, and this inverse transformation can be written as U M N. Now again the double summation, and now V K and L, and then we set a dot product of A conjugation K and L M N, and this K and L starts from 0 to N minus 1, and M and N, this M and N actually is again less than or equal to capital N minus 1 and less than n equal to 0. So if we take this expression, both M and N will vary from 0 to capital N minus 1. N will also vary from 0 to capital N minus 1. So to compute this VKL, this one, then what we need to have this complex multiplication and addition. So that has to be performed on order of capital N square. And you remember that this has to be computed for every value of K and L. Okay. Now where K and L vary in range of 0 to capital N minus 1. That is, K is having a capital N number of values and L will also have a capital N number of values. So to find out single coefficient VKL, we have to have the order of capital N square, number of complex multiplication and addition. So in total amount of computation that we will need it is, in this particular case, is order of capital N to the power of 4. Obviously this is quite expensive for any of the normal size image, because if we get the image size of 256 by 256 pixels or 1K by 1K or maybe 2K by 2K pixel, so we need a lot of computation. So for reducing this computation complexity, for that we have to have some mathematical tools, and where we have this concept of separable unitary transformation. So that's why, as this is too much for us, the computation will be too much, because it's for every K and L, and then again for values of each time, because this is varies from double summation, varies from K and L is equal to 0. So that's why we have a lot of computation in here. अब अगर हम यहाँ पर देखते हैं कि अगर हम इस इक्वेशन को परफॉर्म करें, तो दोनों सिचुएशन में हमारे पास ऑफ जो ऑर्डर आता है वो ऑर्डर ऑफ n 4 आ रहा है. तो उसकी वजह ये है कि हम मल्टीप्लिकेशन भी कर रहे हैं और साथ में हम एडिशन भी कर रहे हैं. तो हमारे जो नॉर्मल एक कंप्यूटेशन के लिए n स्क्वायर आ रहा है, लेकिन जब हम चूंकि 2 टाइम परफॉर्म कर रहे हैं, तो इस वजह से हमारे पास n 4 आ रहा है, जो पावर उसकी आ रही है कंप्यूटेशन ऑर्डर की. तो अब ये क्योंकि बहुत ज़्यादा है और इस पे बहुत ज़्यादा टाइम लगता है, अगर हम सिंपल 256 बाई 256 पिक्सल्स लेते हैं और फिर हम ये परफॉर्म करते हैं, तो क्योंकि जो बिग ओ है उसकी वैल्यू n पावर 4 आ रही है तो उस पर काफ़ी ज़्यादा टाइम लगेगा। अब इसके लिए हम क्या कर सकते हैं, हम सिंपल कोई मैथमेटिकल ऑपरेशन परफॉर्म करते हैं, टूल्स को यूज़ करते हैं, और वो जो है टूल्स उसको नॉर्मली हम यूज़ करते हैं तो हम उसको कहते हैं सेपरेबल यूनिटरी ट्रांसफॉर्मेशन। तो अब वो हम यूज़ करेंगे, वो कैसे यूज़ करेंगे। Now we know that the transformation matrix which is represented by a matrix A, or we have represented this as a AKL, which is M and N. So we can say that this is a separable in a way that if that can be represented in a form of AKM. So this is a separable if we say Km dot BL N, or equivalently we can also say that it can be in a form of A Km dot B L N. Now to see these two sets AKM and BLN, they are one-dimensional complete orthogonal sets of basis vector. Now if we are representing this set of orthonormal basis vector, both AKM and BLN in a form of matrices, we can represent it as, अगर हम इसको अब मैट्रिक्स की फॉर्म में रिप्रेजेंट करना चाहेंगे तो वो कैसे होगा, हम कहेंगे कि ये A K M and K is equal to 0 n minus 1, और सेम इसी तरह B L N L is equal to 0 to n minus 1. तो अब ये हमारे पास आ गए हैं मैट्रिक्स की फॉर्म में, ठीक है। एंड A similarly B both are in a matrix form, so we can say that this is now a unitary matrix. So this should be a unitary matrix, and also B So now we are going to see next that how the separable transformation helps us to reduce the computational complexity. So this should be both of them should be a unitary matrix, and now we can represent it as a form of matrices. So how do we reduce the complexity using this separable transformation? So in that situation, what we do now, in the most cases, what we assume these two matrices A and B to be the same. So they are normally, we assume that they are same. If I take both A and B to be equal to same, then the transformation equation can be written in a form of VKL is equal to double summation A Km UM N AL N, and some M and N equal to 0 from n minus 1. So now instead of using B, we do not use the value of B because we assume that they are supposed to be equal. So if it is equal, then normally we can make the changes with the equation. So now in form of a matrix, this equation can also be represented as V equals to A, U and A transpose, where U is the input image of dimension capital N by capital N. V is the coefficient matrix again of dimension capital N by capital N, and matrix A is a also a dimension capital N and capital N. So in the same manner, the inverse transformation can now be also rewritten as UM N is equal to double summation A conjugation KM V K and L, and then A conjugation L N, and again this K and L start from 0 to N minus 1. So this is the expression for the inverse transformation. Again, as before this inverse transformation, we can see that this also can be represented in a form of a matrix. So if we want to represent it in a form of a matrix, then it can be U, which is equal to A transpose A conjugation transpose V and A transpose. Now this can be the expression in a form of separable transformation. Now what we call this as a separable transformation, and then we will see how to reduce the complexity. अब अगर आप यहाँ पर देखें, अगर हम assume करें कि A और B हमारे पास सेम है, तो इस सिचुएशन में हम यहाँ पर जो B की वैल्यू यूज़ करते थे वो हमने निकाल ली. U जो है हमारे पास ओरिजिनल इमेज है जो इनपुट आ रही है, और उसके बाद अगर हम उसको मैट्रिक्स की फॉर्म में लाते हैं तो वो हम उसको रिप्रेजेंट कर सकते हैं इस तरह. और अगर हम इन्वर्स केस में जाते हैं कि हम इन्वर्स वापस ओरिजिनल इमेज की तरफ जाना चाहते हैं, तो उस सिचुएशन में हम दोबारा U और MN लेते हैं और हम साथ में उसको V की वैल्यू U की जगह यूज़ करते हैं. अब सेम इसी तरह हम इसको भी मैट्रिक्स की फॉर्म में रिप्रेजेंट कर सकते हैं. अब हम क्या करते हैं, हम आगे इसको फर्दर लेकर जाते हैं. एंड यू नो दैट दिस पर्टिकुलर इक्वेशन V इक्वल टू AU ट्रांसपोज this can also be rewritten in a form of V transpose is equal to A so now if you take the multiplication of A and U and then take the transpose of it, then remultiply that result with the matrix A here, which is itself, then what we are going to get is the transpose of the coefficient matrix V. So these two dimensional transformation can be performed by first transforming each column of U with the matrix A and then transforming each row of the result to obtain the row of the coefficient matrix V. Now we know that A is a matrix of dimension capital N. So this is a N by N, and U is also a matrix of dimension N by N. So from matrix algebra, we know that if we want to multiply two matrices of dimension equal capital N by capital N, then the complexity or the number of addition and multiplication in order of capital N cube. So this we call it as a N cube. So now this is the order that we get, because A and U are N by N dimensions. So now first, if we want to take the multiplication of A and U, then this will be of order N3. Okay, and then after that what we do, we take the second operation, and that is to multiply it with the A. And this is also of order N cube. So the total number of addition and multiplication that we need is of order N 2 order of 2N cube. And to compare this with the original configuration that is of order N, if we compare it with this order of N power 4, so we have obtained the reduction of the computational complexity by a factor of capital N. This shows that if the transformation in the form of separable transformation we use it, then it is possible that the computational complexity will be reduced. The final result of the coefficient matrix and will be the same if we are using non-separable transformation or if we are using separable transformation. So there will be no effect on the result. So that's why if we use the separable transformation, then we have the complexity of 2N cube, and that is less than the original, which was order of N power of 4. अगर हम यहाँ पर हम कुछ चीज़ें एज्यूम कर लेते हैं, तो एजम्पशन के बाद हमें ये पता चलता है कि ये A जो है N by N है, तो चूँकि N by N है तो हमें ये पता है कि जब भी हम N by N की कोई भी कम्प्लेक्सिटी आइडेंटिफाई करते हैं तो वो होगी ऑर्डर ऑफ N क्यूब. लेकिन चूँकि हम यहाँ पर दो ऑपरेशंस परफॉर्म कर रहे हैं, तो वो दोनों की सिचुएशन में ऑर्डर ऑफ N क्यूब और ऑर्डर ऑफ N क्यूब आ जाएगा. इस वजह से हम 2N क्यूब ले लेते हैं. तो ये 2N क्यूब जो है हमारे पास लेस है अगर हम ओरिजिनल ऑर्डर लेते हैं N पावर ऑफ 4. अब हम जाते हैं बेसिस इमेज की तरफ. अगर हम बेसिस इमेज लेते हैं तो उसमें हमारे पास कंप्यूटेशन कम्प्लेक्सिटी क्या आएगी. Now we assume that suppose A K star is denoted the kth column of matrix A. So this is the kth column of A conjugate T transpose. Now we can define the A star matrix like in a form of A star K and L is equal to A star K into A star L, and it is transpose. So you will find that the A K star is the kth column of matrix A star transpose. A L star is also the the nth column of the matrix A conjugation transpose. So if I take the product of AK star and AL star transpose, then I can get the matrix A matrix AKL star, and let us also define the inner product of n by n matrix. So the inner product, this is the inner product of n by n. This is F and G. So this we define it as a inner product. Okay, this we have it. Now, so for the inner product of these two matrices F and G can be defined as F and G. So double summation, again same thing, F, M and N, G conjugation M and N, and then M and N starts from 0 to capital N minus 1. Now this transformation equation is nothing but the expression of the inner product, and this inner product can also be an image matrix U. So if we want to say that this is the inner product, we can represent it as a U with the transformation matrix A star KL, AKL and conjugation. So this particular derivation simply says that the purpose of image transformation is to represent an input image in a form of linear combination of a set of a basis image. Now what we do, we will have to compute this VKL. Can be represented as an inner product of the input image U and the KLth basis image is A star. K and L. So this is actually represented as an inner product of the input image U with the KLth basis image A KL star. And because this is the inner product of the input image U and the KLth basis image A KL star, this is also called the projection of the input image on the KLth basis. So we can also call this as a projection of U onto the KLth basis image AKL star. So this is called a projection of input image U onto the KLth basis image AKL star. This also shows that any image input U of the size capital N by N can be expanded using the complete set of N square basis image. So that is the basic purpose of our input of image transformation. Now let us see one example. So let's consider an example of this transformation. Say we have the transformation matrix which is given by A is equal to 1 by square root of 2 1 1 1 minus 1, and we have the input image matrix U, which is equal to 1 2 3 4. अब ये हमारे पास आ गई है इनपुट इमेज A, और ये हमारे पास है जो ओरिजिनल इमेज है. द इमेज मैट्रिक्स इज दिस वन एंड दिस इज द ट्रांसफॉर्मेशन मैट्रिक्स. अब अगर हम ट्रांसफॉर्मेशन मैट्रिक्स को ले रहे हैं, ठीक है. नाउ हाउ we see that how this transformation matrix works with the input image matrix. So if I take the inverse transformation, that should also be able to get back to the original input image U. अगर हम ये ट्रांसफॉर्मेशन परफॉर्म करते हैं तो ट्रांसफॉर्मेशन के बाद अगर हम वापस आना चाहते हैं तो अगर हम ये इन्वर्स लेंगे तो इन्वर्स की सिचुएशन में हमारे पास ये मैट्रिक्स आनी चाहिए, ठीक है. नाउ मैट्रिक्स V विल बी गिवन बाय, अब ट्रांसफॉर्मेशन हम कैसे करेंगे, V विल बी गिवन बाय 1 by 2 into 1 1 1 and minus 1. ठीक है. अगर हम फार्मूला को देखें पीछे तो हमारे पास V की सिचुएशन में हम यहाँ पर ओरिजिनल जो ट्रांसफॉर्मेशन मैट्रिक्स है उसको लेते हैं और उसके बाद हम इनपुट इमेज लेते हैं. इनपुट इमेज हमारे पास है 1 2 3 4 और उसके बाद हम क्या करते हैं, A ट्रांसपोज लेते हैं, ठीक है. तो A ट्रांसपोज इस सिचुएशन में हमारे पास एग्जैक्टली वही आएगा जो A है, A की वैल्यू है, क्योंकि जो वैल्यूज उसमें हैं वो एग्जैक्टली उस पर कोई असर नहीं पड़ेंगे. सो A ट्रांसपोज इज सेम एज 1 1 1 minus 1. So by matrix calculation it will be simply come out to be 1/2 4 6 minus 2 into 1 1 1 minus 1. And now on completion of this matrix multiplication, the final coefficient matrix V will be 5 minus 1 minus 2 and 0. So this is the final values of our coefficient vector V. So now let us see the transformation with the corresponding basis image. So we define the basis image as a K star to be the kth column of A conjugation transpose. Now using the same concept of and from this our basis function we can take as AKL star AKL star. We already defined this, that it can be A K star into A L star transpose. So this is how we had computed the basis image. We have defined the basis image in this particular example where we have all the transformation matrix A is given as, so this is given as 1 by 2, 1, 1, 1 and minus 1. We can compute this basis image as a 0, 0 star is the 0th basis image will simply be half into the basis vector 1 and 1 and then 1 and 1 transpose. Similarly, we can also compute, this will also give us, so what will be the output? 1 by 2, 1, 1, 1 and 1. So similarly, we can also compute for A star 0 and 1, that is the 0 and 1th basis image, we will give a half into 1 minus 1, 1 minus 1, and which will be same as S star 1 and 0. That is the 1/0th basis image. And we can also compute a 1 star is equal to half 1 minus 1 minus 1 and 1. We can compute these basis image from the column of A conjunction transpose. So these are the values that how we do it with the basis image. So once we are computing with the basis image. Now to see what will be the results in case of inverse transformation. So you remember that the transformation coefficient matrix V was actually 5 minus 1 minus 2 and 0. So this was the coefficient vector that we got. So this was our value that we got it. So by inverse transformation is a conjugate transpose V A conjugate. So this is equal to, if we put the values in it, half 1 1 1 and then minus 1, then we put the value of V 5 minus 1 minus 2 and 0, and then again a conjugation which is 1 1 1 and minus 1. So if we compute this, the matrix with the matrix multiplication or the expression that we will get at the end will be 1, 2, 3 and 4. And this is, if you remember, this was our matrix U here. So our original matrix U was 1, 2, 3, 4, and then we take the inverse to get the original image. For that we already have 1, 2, 3 and 4. So this shows that if we want to compute, then after computation we can get the original value. Now if we want to see some visualizing the discrete cosine transformation basis image, then there are some examples that there are different types which are real and imaginary that we will discuss in the Fourier transform when we study that. So this is the basis image of dimension 8 by 8, in total 64 basis image. And for every basis image there are 8 by 8 pixels, like there are again 8 by 8 columns and rows. So there are some real components and some are imaginary components. Again, there are another example that we can see that after applying different kind of basis image, then this is another type, and we also see that there are 64 images because it's 8 by 8 grid, and then 8 by 8 grid, each image is a basis image and which represented also by 8 by 8 pixels. And then we have some basis image transformation, and there are many different types of it, like Walsh transformation and Hedmard transformation. तो यहाँ पर हमारे पास मुख्तलिफ़ किस्म के ट्रांसफॉर्मेशन आ रहे हैं जो हम देखते हैं कि हम इसको अप्लाई करेंगे आगे जब हम नेक्स्ट लेक्चर्स में देखेंगे. तो यहाँ पर सिर्फ पर्पज़ ये था इसके दिखाने का कि हम ये देखें कि अगर हम इसको कंबाइन करते हैं तो सेट ऑफ बेसिस इमेज किस तरह शोज होंगी, और each basis image will be weighted by the corresponding coefficient in the transformation coefficient VKL. VKL is the inner product of KLth basis image. अब ये हमने पीछे लेक्चर में डिस्कस किया कि हमारे पास VKL क्या है और हम उसको इनर प्रोडक्ट ऑफ KLth बेसिस इमेज किस तरह उसको हम रिप्रेजेंट कर सकते हैं. तो यहाँ पर हमने ये सीखा कि अगर हम सिंपली बेसिस इमेज को लेते हैं और फिर उसके साथ हम अप्लाई करते हैं ट्रांसफॉर्मेशन, तो हम ओरिजिनल इमेज की तरफ वापस जा सकते हैं. So now we will move to the next topic, that is image transformation, that we know already that there are many time image processing takes are best performed in a domain other than the spatial domain. So what we need to do, we need to have these key points, the key steps that transform the image. So first, from a spatial domain, what we do, we transform the image, and that we call it as a TUV, and then we perform the operation R, whatever the transformation operation that we perform. So carry the task in the transform domain, and then after that apply the inverse transformation, so that we can have the spatial domain image again, the function that we want to have as a g of xy. So for that reason we need to have this inverse transformation. So there are many different other transformation methods, and for that the transformation kernels that are very important. So the forward transformation that we use, that is a TUV, and then we have Duhamel summations because of the two dimensions that we take this image as a, or maybe the transformation as a m by n dimensions. So that's why the summation starts from x is equal to 0 till m minus 1, and then y is equal to 0 till n minus 1, and then we have the forward transformation kernel that we normally use, and u is equal to 0 till 1 and m minus 1, and we have as a 0 to 1 till n minus 1. And then as we need to have this inverse transformation, because in here we know that the inverse transformation is very important, so that we can take the original effect. So for that reason we also need to have this inverse transformation, and the formula that we use normally is somehow related like this. Then we have different kernel properties. Kernel is said to be separable if we have the formulation in this situation that r x y u v is equal to r1 x u, r2 is y and v. So we take these two as a separable. So if we can make it as a separable, we can remove make it separate. अगर हम अलग कर सकते हैं उसको, तो फिर हम कर्नल उसको सेपरेबल कर्नल कहते हैं. और दूसरे सिचुएशन में सिमेट्रिक भी हम उसको कहते हैं कि जब हमारे पास r1 हो और x u को हम लेते हैं और r1 y v को लेते हैं, तो इस कर्नल को हम सिमेट्रिक भी कहते हैं. हम डिफरेंट किस्म के नोटेशंस यूज़ करते हैं. फोरियर ट्रांसफॉर्मेशन को हम ज़्यादा डिटेल में नहीं देखेंगे, लेकिन उसके जो बेसिक फंक्शंस हैं जो नॉर्मली हम यूज़ करते हैं इमेज प्रोसेसिंग के लिए, तो हम वो देखते हैं. एक हमारे पास आ जाता है कि कंटिन्यूस फोरियर ट्रांसफॉर्मेशन नॉर्मली हम यूज़ करते हैं. फिर वो क्योंकि कंटिन्यूस फोरियर ट्रांसफॉर्मेशन हमें चाहिए होता है बेसिक फार्मूले के लिए, तो हम बेसिक फार्मूला लेते हैं कंटिन्यूस फोरियर ट्रांसफॉर्मेशन. फिर हम देखते हैं कि नॉर्मली इमेज प्रोसेसिंग में हम डिस्क्रीट फोरियर ट्रांसफॉर्मेशन यूज़ करते हैं, और फिर उसके बाद फास्ट फोरियर ट्रांसफॉर्मेशन हम मुख्तलिफ ऑपरेशंस के लिए यूज़ करते हैं. सो द प्रॉपर्टी ऑफ ट्रांसफॉर्मेशंस हमारे पास क्या है? दे convert a functions from a one domain to another with no loss of information. तो हम फोरियर ट्रांसफॉर्मेशन नॉर्मली यूज़ करते हैं इसलिए कि हम उसमें इंफॉर्मेशन का लॉस ना हो हमारे पास, और जो हम ट्रांसफॉर्मेशन करें तो वो वन फॉर्म ऑफ डोमेन टू अनदर फॉर्म ऑफ डोमेन करते हैं. सो फोरियर ट्रांसफॉर्मेशन में का जो बेसिक फार्मूला हमारे पास आता है वो एफ ऑफ डब्ल्यू आएगा, और इज इक्वल टू 1/2 पाई बाय अंडर रूट, and then we have the integral from minus infinity to infinity f of t e to the power minus I w t and dt converts a function from the time or spatial domain to the frequency domain. So in this situation what we do, because we need to convert from one domain to another domain with no loss, so what we do here, we convert from time, which we also call it as a spatial domain, to a frequency domain. So time domain tells us how properties air pressure in sound function, for example, change over time. So this is the air pressure if we have in time domain, how the properties changes. So if we have this image, then what we do, we have this plot of it as a time and as a pressure. So here we have this amplitude, and then we see the frequency number of cycles in 1 second, that is 200 gigahertz. Hertz. So in frequency domain, what we tell us properties amplitude and change over frequencies. तो हम जब जाते हैं frequency domain में, तो वहाँ पर हमारे पास आते हैं कि हम देखते हैं कि उसका amplitude क्या है और frequency किलोहर्ट्ज़ में क्या आ रहा है हमारे पास. सो कंटिन्यूस फोरियर ट्रांसफॉर्म जब हमने बात की थी, तो उसके लिए हमारे पास बेसिक जो फार्मूलेज आते हैं वो दो किस्म के होते हैं, एक फॉरवर्ड और एक इन्वर्स, क्योंकि हमने देखा कि हमें इन्वर्स ट्रांसफॉर्मेशन की ज़रूरत पड़ती है. सो ट्रांसफॉर्म्स ए सिग्नल that is a function from the spatial x domain to a frequency u. So if it is a single dimension, one dimension, then in that situation we use simply the frequency x, and we have the frequency u as a domain, as a output. So what we do, we have forward transform, that is f of x is equal to f of u, and then we have the transformation function, Fourier transformation, that is the integral minus infinity to infinity f of x, and then e to the power minus j 2 pi ux and dx. And same is the inverse. So for the inverse, what we do, we have f of u, and then f of x is equal to that is the integral from minus infinity to infinity, and then f of u e to the power j 2 pi ux and d, where e plus minus j theta is equal to cosine theta plus j sine theta. That is a plus minus, so what we have here as a continuous value. So in image processing, instead of time domain, spatial domain or normal spaces. So instead of in image processing, what we do, instead of time domain, what we do, we have a spatial domain, that is a normal image space, so in which space we have this image. And in frequency domains, space in which each image value at image position f represents the amount of that intensity value in the image I vary over a specific distance related to f. So what we do in a frequency domain, that the value of some specific point that positions at f represent the amount that the intensity value in image I vary over the specific distance related to f. So whatever this, अगर हम कोई point लेते हैं तो वो point की intensity की value हम identify करते हैं उस image के अंदर relative to its position. So वो position उसकी कहाँ पर है तो उसकी intensity को हम identify करते हैं. So if there is a value 20 at the point, so there is at point 20 that represent the frequency 0, 1 or 1 period over 10 pixels. So this is the location, and then we have this frequency. This means that the corresponding spatial domain image I, the intensity value vary from dark to light and back to dark over a distance of 10 pixels, and that the contrast between the light and darkest is 40 gray levels. So this is what normally we check in our application. So spatial frequency of an image refers to the rate at which the pixel intensity changes. So in spatial domain of the image refers to the rate at which the pixel intensity changes, जहाँ पर जो हम वो rate identify करते हैं कि जिससे वो pixel की intensity change हो रही है, तो उसको identify करने के लिए normally हम Fourier transform apply करते हैं. In picture of right, high frequency near center, तो हम यहाँ पर देखते हैं कि high frequency है near center and low frequency at corners हमारे पास आ रहे हैं. सेम इसी तरह हम उसके एप्लीकेशन देखते हैं. सम स्पेसिमेन इमेज है हमारे पास, हम फिर यहाँ पर देखते हैं कि अगर हम उसके ऊपर डिफरेंट फिल्टर्स अप्लाई करते हैं जिसमें हम उसकी ट्रांसफॉर्मेशन देखते हैं, फोरियर ट्रांसफॉर्मेशंस की वैल्यूज़ देखते हैं कि वो क्या हैं, कौन से ऐसे वैल्यूज़ हैं जिसको हम आइडेंटिफाई कर सकते हैं कि वो पिक्सेल्स की जो इंटेंसिटी है वो किस लेवल से चेंज हो रही है. जब हमें वो मिल जाता है तो हम उसके थ्रू फिर इमेज को फ़िल्टर कर सकते हैं. यहाँ पर आप देख सकते हैं कि बहुत ज़्यादा नॉइज़ है, लेकिन जब हमें ये वैल्यूज़ मिल जाती हैं तो इन वैल्यूज़ के थ्रू हम फ़िल्टर अप्लाई करते हैं और उससे हमारे पास इमेज काफ़ी ज़्यादा इन्हांस हो जाता है. So example of noise reduction using Fourier transform. So this is the original image, and what we do, we apply the Fourier transform. So we identify the change in the intensity values, and then what we do, we band pass filter, we take these values and we apply it using this band pass filter, and after that when we apply this transformation, we have the image as a noise removed. So continuous Fourier transform, the basic formula that we have now, transform a signal function from the spatial x domain to a frequency domain, and this we already know. This is the in the continuous Fourier transform, and once we want to have it as a 2D, then in a 2D, because this is in 1D, so in 2D what we do, we have this formula. Assume that f of x y is m and n dimension. So for that reason, our Fourier transform function, forward Fourier transform, will be f of uv is equal to 1 by mn, and then instead of one summation we use two summations, double summations, and x and y start from 0 to m minus 1 and n minus 1, and then this area we also change it, because in the one dimension we have only one values, but in here as it's two dimensions, two values, so that's why we use the m and n. And again inverse, for the inverse we use this f of x y is equal to again summation and then f of u v, which was here, and then we use the same formula, and x varies, x and y both starts from 0 to n and m minus 1. And then if we want to draw it in a Fourier transform as a two-dimensional rectangle function, then what we see, we have this a as an image of f of x and y. So f of u and v, that is in two dimension, we have the values of u and v, and then if we want to draw it as a this is in a three dimension, but in here if we want to draw it as a two dimension, then we can see the intensity values. Now extended discrete Fourier transform to 2D, that is the image we have. Then if we take it as a value of 3, then we can see that there are different sign functions that we can use. So plus 5 and then plus 10 and then plus 23. Here is also visualizing of DFT. Typically we visualize f of uv as a values. This dynamic range of f of uv is typically very large. So what we do, we apply some stretching. So for applying some stretching, what we do, duv is equal to c log 1 plus f of uv. This is the absolute values, and this c is actually a constant value. So this is the original image, and then we have the Fourier transform, and this is in Fourier transform. If we see the absolute values, then it's like this, and then if we stretch it, so after stretching, applying this specific formula, then we can have visualizing with very clearly. So what are the basic properties of translation? We have this f of xy, this we already know, and we convert it into f of uv, which is in a Fourier transform. So translation in a spatial domain. So in a spatial domain case, if it is a two dimension, then f of x minus y naught, y minus y naught, then we convert it as a f of uv e to the power minus j 2 pi ux naught plus v y naught divided by n. And if we translate in frequency domain, then the formula is something like this. So again we have the DFT properties, that is to translate. For translation, f of xy minus 1x plus y, that is f of u minus n by 2 v minus n by 2. If we have this dimension n by n, then we can use this only n. So this is the original image, and then we have the translation, and then we have, after the translation, we can see the results. And this is another translation types, if it is a horizontal or if it is in a 45-degree angle. So rotation at f of x by theta rotates f of uy by theta. So we summarize our lecture here. So today we learned analyze the computational complexity of image transformation operations, and then we also learned the separable transformation, that what are the separable transformation, and after that we learned the computational complexity of reduction of the separable transformation. And we also learned that if we have the Fourier transformation, we want to apply the Fourier transformation, then there are Fourier transformation, and we need to transform it into digital Fourier transformation, and after that we also need a fast Fourier transformation for different operations. So there are many usage of Fourier transformation in image processing, and we need to know the basic formulas for it, and then if we know the basic formula and also its application, then we can use it whenever we have the need of it. So the conclusion of today's lecture is that we need to have this basic transformation complexity, and also we need to know the basic transformation as a Fourier transformation. So until now we will finish here, and we will continue in the next lecture with other topics. Allah Hafiz.